Hi guys, have you heard about maximum power transfer theorem? You must have heard about it since it's an important theorem in network analysis. Today, I came up here with a video which will share everything about maximum power transfer theorem. It's me Abhisha and you are watching me on our channel Crack Easy. So, without wasting further time, let's get started. In fact, maximum power transfer theorem tells us about the condition at which maximum power transfer can take place. It says a network delivers the maximum power to a load resistance RL when RL is equal to the Thevenin or Norton equivalent resistance of the network. Got it? Hope you remember what is Thevenin or Norton equivalent resistance of a network and how to calculate their values. If you have any doubts regarding that, please do watch my videos on Thevenin's theorem and Norton's theorem. Let us now focus on one practical application of maximum power transfer theorem. As you know, in radio communication, we have to transfer the signals from power amplifier in the transmitter section to transmitter antenna efficiently. If we match output impedance of power amplifier to the antenna impedance, then maximum power transfer takes place there. Alright? So, if we choose source and load impedances of these type of systems based on maximum power transfer theorem, then we will get a system with better performance. Okay, let us now focus more on the concept of maximum power transfer theorem. Here you can see a source network and load resistor RL connected between terminals XY. In this diagram, this source network is replaced with its Thevenin equivalent circuit where a voltage source VTH is connected in series with Thevenin equivalent resistance RTH. IL is marked as current through this load resistor RL. Based on maximum power transfer theorem, this source network delivers maximum power to this load resistor RL when RL is equal to RTH, and the amount of that maximum power can be mathematically expressed as Pmax is equal to VTH square by 4 RTH, where Pmax is the maximum power, VTH is the Thevenin equivalent voltage, and RTH is the Thevenin equivalent resistance of the source network. Alright? Let me now take you to some problems based on maximum power transfer theorem. In the circuit shown, determine the value of load resistance when the load resistance draws maximum power. Also find the value of maximum power. You can see the circuit here. A 50 volt source is series connected with a resistor 25 ohm. RL is the load resistor. So this is our source network and this is our load resistor. Our task is to calculate value of this load resistor so that source network delivers maximum power to load and also the value of that maximum power. By inspecting this source network, you can see it's already in the form of Thevenin equivalent circuit. So we can directly find the values of VTH and RTH from this circuit. What are the values? Can anyone tell me? VTH or Thevenin equivalent voltage is 50 volts and RTH or Thevenin equivalent resistance of the source network is 25 ohm. By maximum power transfer theorem, a source network delivers maximum power to a load resistor when RL is equal to Thevenin equivalent resistance of the network. So we can write for maximum power transfer RL is equal to RTH, that is equal to 25 ohm, and the amount of maximum power Pmax is equal to VTH square by 4 RL. By substituting the values of VTH and RL, we get Pmax as 25 volts. Alright. Thus we calculated the values of RL and Pmax. Moving on to next question. Find the value of R in the circuit given such that maximum power transfer take place. What is the amount of this power? The circuit is given here. As usual, let us first analyze this circuit. Here, this is the source network and this is load resistor. Here also our task is to calculate value of this load resistor so that this source network delivers maximum power to this load resistor and also the amount of that maximum power. By maximum power transfer theorem, a source network delivers maximum power to a load resistor. Then load resistor value is equal to Thevenin equivalent resistance of the source network. So what we are going to do is first we find out the Thevenin equivalent circuit of this network. Then we equate RL to RTH so that maximum power transfer takes place. And for obtaining Thevenin equivalent circuit of a network, we are supposed to calculate two quantities, Thevenin equivalent voltage and Thevenin equivalent resistance. Let us first focus on Thevenin equivalent resistance. It can be obtained by setting all independent sources present in the network to 0 and then calculate internal resistance of the source network looking from open circuited load terminals. Here we have two independent voltage sources, this 6 volt source and this 4 volt source. After short circuiting these sources, we get a circuit like this. AB are the open circuited load terminals. When we look from this side, this 1 ohm and this 2 ohm are connected in parallel. So we replace this portion of network with its parallel equivalent resistance 0.66 ohm. Again, when we look from this side, this 0.66 ohm and this 5 ohm are connected in series. So we replace this portion of network with its series equivalent resistance 5.66 ohm. Finally, you can see this 5.66 ohm and this 1 ohm are connected in parallel. So we write RTH, Thevenin equivalent resistance, as 1 ohm parallel 5.66 ohm. That is equal to 0.85 ohm. Alright. Thus we calculate at RTH. So what we are supposed to do next? We have to calculate VTH, Thevenin equivalent voltage, which is nothing but the open circuited voltage across open circuited load terminals. So here AB are the open circuited load terminals. By analyzing this network, you can see 3 loops here. Let us consider this as first loop, this as second loop and this as third loop. I1 is marked as loop current in first loop in clockwise direction, I2 as loop current in second loop in clockwise direction. Since these terminals are open, there is no loop current in this third loop. Then we mark polarities of voltage drop across each resistors according to the direction of assigned loop currents. Now we are going to write KVL in this first loop in clockwise direction. Starting at this point, first we observe this 4 volt voltage source with the polarity mark in the order minus plus. So we start our KVL equation with the minus 4. Then this 1 ohm, correspondingly we add a term plus 1 into I1. Finally, the voltage drop across this 2 ohm. Since we are writing KVL in first loop, the total current through this 2 ohm should be taken as I1 minus I2, and correspondingly the voltage drop 2 into I1 minus I2. So we added term I1 minus I2 into 2 to our KVL equation. So we get minus 4 plus I1 plus I1 minus I2 into 2 is equal to 0. Alright. Then by rearranging these terms we get 3I1 minus 2I2 is equal to 4, which is labeled as equation number 1. Next we apply KVL in second loop. Starting at this point, first we observe the voltage drop across these 2 ohm. Since we are writing KVL in second loop, the total current through this 2 ohm is taken as I2 minus I1 and correspondingly voltage drop 2 into I2 minus I1. So we start our KVL equation with I2 minus I1 into 2. Then the voltage drop across this 5 ohm, which is nothing but 5 into I2 with the polarity mark plus minus. So a term 5 into I2 is added to our KVL equation. Finally, the voltage drop across this 1 ohm. Correspondingly, we add a term 1 into I2 to our KVL equation. Thus we get I2 minus I1 into 2 plus 5I2 plus I2 is equal to 0. By rearranging this we get 8I2 minus 2I1 is equal to 0, and it is labeled as equation number 2. By solving these two equations we get values of I1 as 1.6 ampere and I2 as 0.4 amperes. Alright, let us now write KVL in the third loop. Starting at this point, first we observe this 6 volt voltage source with the polarity mark in the order minus plus. So we start our KVL equation with minus 6. Then the voltage drop across this 1 ohm, which is nothing but 1 into I2 with the polarity mark minus plus. Correspondingly, we add a term minus 0.4. Finally, the open circuited voltage VAB or VTH with the polarity mark plus minus. Correspondingly, we add plus VAB. So we get minus 6 minus 0.4 plus VAB is equal to 0, or VAB or VTH is equal to 6.4 volts. Alright. Thus, we calculated the values of RTH and VTH. Based on maximum power transfer theorem, we can say that value of RL at which maximum power transfer takes place is equal to RTH, that is 0.85 ohm, and that maximum power is equal to VTH square by 4RL. By substituting the values of VTH and RL, we get it as 12 volts. Got it? That's all for today. Thanks for watching. Thank you.